and gentlemen, recording has begun. So yesterday, we got into our unit dealing with waves, light, and sound. So first thing we did yesterday was we introduced what a wave was. So what is a wave? It's a wave is a way of transferring energy, or it's energy moving around. Chris.
I can tell you something about waves that happened yesterday.
Nice.
I was in my front yard, and
Okay.
down the street from the school.
Yep.
And I'd see a dribble, and while it was going out, to make a sound.
Nice. We'll talk about that more next week when we talk about sound and light. So. But they're both waves, but the light waves travel way faster than the sound waves do. So you see it happen first, and then you hear it a little bit later. Yeah, it's actually when I played basketball in my yard, but their house right across the street from us, like their driveway is lined up exactly with ours, so their garage is lined up exactly with ours. So it echoes all the time. Like I bounce it, then I hear it again. Like it's not real far away, but yeah, it's kind of cool. All right, waves. So we said that a wave is a disturbance, but a wave will do what? What is the main purpose of a wave, or what does it do?
Carries energy.
Carries energy, right? Which means in order for a wave to start, we have to do some work. Okay? We talked first yesterday about mechanical waves. And we said that what is our definition of a mechanical wave?
The medium to traffic.
That's a specific type of mechanical wave. What is a mechanical wave?
Material.
It has to travel through
Material.
medium. You especially can't be talking out of turn. You're right next to the microphone. What is this, like 3 years ago?
Sorry, Nick.
Easy, it's not recording.
You hear about him,
Alright. So yesterday we talked about a mechanical wave. So a mechanical wave has to travel through something. We referred to that something as what? The medium. Then we talked about two specific types of mechanical waves. The first type of mechanical wave we talked about was a transverse wave. And by definition, the transverse wave is where the medium vibrates at right angles to the motion of the wave. Because you guys are early in the day, sometimes I forget about really good examples that illustrate concepts really well, and I forgot about that yesterday. Okay? The best example I can give you of a transverse wave, or of waves in general, is when you do the wave at like a football game or a baseball game or something like that. Okay? So, first, let's talk about the start of the wave. Right? How does the wave start? Right? First, before someone gets up and stands up, somebody else goes down to the front row and does what? Hey! We're going to do the wave! Generally, that person is alcohol-induced, but, whatever. Okay? So, someone gets down there and they're like, all right, here we go! 1, 2, 3! Right? So, when we start off a wave, we said that a wave starts with what? It starts with work, or it starts with a disturbance. Is there a disturbance creating that wave?
Yes.
Most certainly, okay? Whether it's alcohol-induced or not, generally it is, but, whatever, okay? So, we said that a wave also transfers energy. The disturbance guy that is starting the wave, does he have energy? Is he energetic?
Yes.
He is, most definitely, right? And he transfers that energy to the people around him. Right? Then, what happens next? Those people transfer energy to the next people, right? Pretty soon, guys on the other side of the stadium are excited and share in alcohol-induced disturbance guy's excitement. But did alcohol-induced disturbance guy have to run over to the other side of the stadium and say, hey, get excited? No, he didn't have to, right? The energy is transferred, but did any matter actually go anywhere? No. When you do the wave, right? When you do the wave, what do you have to do?
Get up.
You stand up and then sit down. Right? Where do you end up? after the wave passes. Exactly where you started. Okay? Might be a little, side, okay? But we talked about the idea that the medium will vibrate, but it doesn't actually go anywhere. Right? In the case of the wave at the stadium, what's the medium? What's the wave traveling through? People, right? The people in the stands are the medium. That's what the wave is traveling through. And if you look at what you do when you do the wave, right? You stand up and you sit back down. Do you actually go anywhere? You're in no different place after the wave passes than before the wave got there. Okay? Then, if we talk about specific types of waves, right? When you do the wave at a sporting event or whatever, okay, the wave travels along the stand, sideways. But how do you move?
Up and down.
You move up and down. That's a transverse wave. Because you're moving up and down. You, as the medium, are moving up and down as the wave is traveling sideways, right? Perpendicular. Okay? Does that work there?
Yeah.
Okay. I mean, it's really like a great example of all the things that we talked about.
Plus it's called the wave.
Plus, it's called full wave. So we really should probably talk about it.
We do it in
About
class.
you all have been doing it in class, right? Yeah.
No.
Let's start it.
So,
Go ahead.
what do you mean when the wave causes the medium to vibrate at frequency?
Okay, so in that case, right, when we talk about right angles, if we talk about the wave, right, the wave is traveling along the stands, right? It goes from section to section to section to section. But the people, the medium that are carrying the wave, you stand up and you sit back down, right? So you're moving up and down as the wave is moving sideways. Does that make sense?
Yeah.
All right. At the end of class yesterday, we talked about a longitudinal, or a compression wave. And we said that this is where the medium will vibrate parallel to the direction of the wave movements. So this would be a situation where, like, if you were lined up outside the gate before the gate actually opened, and somebody in the back started pushing, right? They run into you, but what does that cause you to do? Run into the person in front of you. Then they run into the person in front of them, right? But now in this case, you move forward because you got pushed from behind as the wave is moving forward. Does that make sense? Okay. Somebody else in the earlier class actually brought up a really good example. You know those like punching bags that you had when you were a kid? They like look like a clown and they have like, you put like sand in the bottom of them and you hit it and it like falls down but then it comes back up.
Oh, yeah.
Yes, no, maybe.
Yeah.
Okay.
Kind of.
No.
I
Anyway.
didn't have one, but I know it.
You know what I'm talking about. Okay. So if you, maybe that was a boy thing, I don't know, but whatever. Okay. But if you lined up like 10 of those, okay, and you hit the first one, boom,
All of them.
right?
Oh,
It would run into the next one. But where does it go after it runs into the next one? It pops back up, and it ends up where? Right back where it started.
But it's not the same
So
like
kinda like a
dominoes,
movie
because they
straight
go
up.
back
Right.
to it.
Dominoes are kind of like a compression
But it's
wave,
not all the way.
but they're not exactly that way because when a domino falls down, it doesn't go back to the way that it started. Yeah, Elson, exactly like you said, right? It doesn't come back up, right?
Isn't Newton's cradle a compression?
Kind of, yeah. Although it sort of stops, and then that one last one, like the ball in the end doesn't have anything to pass it on, but yeah, during there it's kind of a compression wave. Yeah, it's just really fast and traveling through a solid. So. All right, we good? Good. Go.
Wait, and that one, people are touching each other. Like, is that?
No, in this case we are in mechanical wave. A mechanical wave basically requires that there's touching, because a mechanical wave, Caroline, is basically conduction. Remember we talked about the 3 types of energy transfer?
Yeah.
A mechanical wave is pretty much conduction. You pass the energy on to the person next to you, right? Now, technically, with like when you do the wave at a sporting event, you don't actually touch the person, like you're
Yeah.
there.
Oh, so it's just that the first person isn't like going all the way.
Right. Yes, the first person, like the alcohol-induced disturbance guy
Yeah.
doesn't have to run over to the other side and tell you to stand up.
Because we passed it.
Right. Everybody passed the energy along.
Okay.
And his energy got to you without him actually having to go there.
Okay.
But to pass the wave on from one person to the next, basically there's some conduction. Like nobody actually moves anywhere.
So the wave has to like come back to its initial point, or
The medium has to come back to, like, the people in the stands have to come back to their initial point.
sitting down.
Yeah. Like, the wave itself will keep going as long as there's energy to transfer, right? When does the wave eventually die out?
When there's like a not fun crowd.
Well, when people are kind of like, all right, I'm done with this, all right? Their alcohol-induced disturbance guy's excitement is no longer traveling through the crowd, right? It's just gone because, yay, woo, we did this 4 times, yeah. But anyway, that's when a wave dies out. It doesn't necessarily die out when it gets back to where it started. It dies out when the energy goes away.
Okay.
Does that make sense? All right. With that being said, let's talk about how we describe waves, or what some of the properties of those mechanical waves are. So first, let's talk about periodic motion.
Why did you leave your electron?
We'll talk about electromagnetic waves next week. So I forgot to change my outline. All right. So first, if we say that a motion is periodic, what is that implying? Not always. Okay, I'll give you that.
It's a
So it's like on a
It's Sam, what'd you say? It's like on a schedule, and it happens at regular intervals. Okay? Things like the rotation of the Earth. Right? The rotation of the Earth happens on a regular schedule. Or the revolution of the Earth as it goes around the sun happens on a regular schedule. If we put this block on the end of a spring, we scrunch up the spring and we let it go, the block's going to shoot out, right? And then it's going to shoot out a little further, right? But then it's going to start coming back, okay? And it will do that at a nice regular interval, okay? Why? Because that's how this spring works. This spring sort of pushes it on the way out and then pulls it back in, and then pushes it on the way out and pulls it back in. Okay?
so the block is attached to it.
Yeah, the block's attached to it. Yeah, kind of like a yo-yo in a way. Yeah, initially, right? We said the wave won't start, or the disturbance won't start, Mary, until we do what? Until we do some work on it. Okay. But there are things that we use to describe this periodic motion that we also use to describe waves. Chris, go ahead.
Back to the block.
Yep.
Start.
Yep.
What if that one say like stop?
Yes. Because, yeah, so that also actually, that's a good question to bring up in a little bit. We'll talk about the next one of these terms here. Okay.
Wouldn't that mean like it would be like the interval?
Right. No. Actually, what we find out is that the time interval actually stays the same. Just how far the block goes changes.
When it says example, should we write down the
Earth rotating, Earth going around the sun. Sam, here. Pendulum on a grandfather clock. These are all periodic motions.
Oh, it's the bird that stops.
Say,
Does
well,
that ever stop? Why does it never stop?
it does stop
When did it stop?
when friction and air resistance slow it down. So if you have a grandfather clock that actually depends on the pendulum, a lot of cheap grandfather clocks that have a pendulum, they really don't rely on the pendulum to keep time. They have a battery, and I'm saying that because my parents have one of the cheap grandfather clocks. And, it has a pendulum, but it works on a battery. So anyway, but because it doesn't actually depend on the pendulum, the pendulum's basically just there for show. Okay, but if you get an expensive grandfather clock, it will depend on the motion of the pendulum.
Yeah, but
So if the pendulum stops,
Then there's no time.
the clock doesn't run.
Oh.
So you have to every once in a while make sure you give it a little push to keep it going.
Don't you have to put it at like a certain time?
Not necessarily, as long as you do it before it stops, you're okay. Because even when it slows down, it doesn't swing as far. Okay, if we go back to this one, okay. What we find out is that this pendulum will take the same amount of time to do this as it does to do this. That how far it swings doesn't
Oh, like in time
influence the time it takes to go.
But if you get them pushed, it can go faster.
No, because the length of the pendulum stays the same, and that's the determining factor. Okay. So, here, it won't go faster, it will go farther up. Okay? Like a kid on a swing. If you start pushing them, right, they don't necessarily, it doesn't take any shorter for them to get back to you. They just go higher on the other side. So the time is exactly the same. Okay? So, period. We use capital T to represent period. Period is the time that is required for one full cycle. Now, sometimes the one full cycle is kind of tricky. Right? On a pendulum, that means if I start from here, I got to go all the way over there and all the way back. Okay? If you're talking about something spinning around in a circle, that's pretty easy what one full cycle is, but make sure we get the one full cycle part. Okay? Alright, so that's period. The time it takes the object to return to its starting position. It's a time. Okay? Sometimes, in some instances I should say, it's not practical for us to measure the period of an object's motion, an object's vibration. So in that case, we look at the frequency. We use lowercase f to represent the frequency. Okay. Like its name suggests, frequency is the number of cycles that occur in 1 second. Technically, it's the number of cycles that occur in a given amount of time, but we usually say that time is 1 second.
cycles like there and back.
Right. So, Allison, how many times does this pendulum swing from there and back in 1 second?
Will it always be like a full one?
No.
Will it...
No, it doesn't necessarily have to be a full number. It doesn't even technically need to be a whole number,
Yes,
right?
yes.
If it takes 1 second for it to go from this side over to this side,
And it went...
it's only completed half of a cycle in 1 second. Okay?
So it has to be going really fast for it.
Yeah, it depends on the vibration. Okay? So, frequency is measured in something that we call hertz. Spelling it out is H-E-R-T-Z. We abbreviate it with Hz. But it stands for cycles per second. How many vibrations or how many cycles does it make every second? So Allison, if we talk about like the rotation of the Earth has a very low frequency because in 1 second it doesn't go very far, right? But, and this is important, especially when we get into some lab stuff we're going to do tomorrow. We said that in order for a wave to be created, what has to be done? Some kind of work, some disturbance has to do work. The frequency of the wave will match the frequency of the vibrating source that produces that wave. The frequency of the wave will match the frequency of the source, the vibrating source that produces that wave. Where's my music people? Okay, middle C. Gosh, you remember? Do you know the frequency on middle C? I think it's 420 or 440 or something like that. Okay. So let's say. Okay. Come on.
Were you in the band or something like that?
I did play band from like 6th grade to 9th grade.
What?
And I got like in 9th grade I got like my fine arts credit and then bailed on it.
What?
I played the cornet. So it's a small trumpet basically, similar to the trumpet.
Pretty good.
I was alright.
You like first chair?
In middle school I was the first chair. Yeah.
Oh,
And I wonder how many
You know, I think there was like 5 or 6.
Don't underestimate great.
So, let's say that whatever note this is, I don't know if this is middle C or somebody said this was A, but I can't remember, whatever. Okay. If there is a note that has a frequency of 440 hertz. That's supposed to be 0.
That's a lot.
That's a lot.
In one
That means, so if we're on a piano, right? Or neurons, do you play the piano yet? Yeah. Okay. So if you hit the key for middle A or whatever note that is, I should really look it up, but whatever. Okay. If you hit that key for middle A, the piano string vibrates back and forth 440 times every second.
holy
Wow.
crap.
So this is 440 cycles for every 1 second. If you sing this note, okay, your vocal cords vibrate back and forth 440 times every second. That's what our ear, Grace, our ear picks up that many vibrations per second as whatever note that is. I can't remember what the note
So
is.
it's like a less number to like a lower.
Yes, and lower. We'll talk more about that when we get to sound next week. But the pitch of that sound is determined by its frequency. So if you have a note that is higher, okay, it's vibrating more times per second, and that your ear picks that up as a different note. So like on a guitar, like the 6 strings on a guitar that play the different notes, they each vibrate at a different
They
frequency.
have different numbers.
They have different numbers.
Wait, does that mean the seconds that's in would it move 880 cycles? per
That would be
second?
like whatever.
Yeah, but what?
I don't know if that's the. I don't know, Sam. I don't know. Yeah, I don't think it's. I don't think it's a direct relationship like that. Like that's not A on the next scale. It doesn't work quite like
It
that.
just keeps
But,
going
But-
like
the
40.
but it will definitely be a higher pitched sound. Okay. Great. Go ahead.
Isn't there like friction though? Like if you play a key, like it won't
Yes.
play forever.
Hold on, though. That doesn't affect. So, Niraj, just because I started with you, right? So, Niraj, you hit the A key, right? And it plays that note. Eventually, what happens to that note? It dies out. It gets quieter. But does the pitch of the note change? It's still A. It's just a quieter A. So a different property of the wave is changing, which we'll get to in a little bit. Okay? Go ahead.
Does this affect the pitch?
Yes, this is what your ear picks up as pitch.
So like when something is like off, like when you have to tune something,
It's
like
not vibrating at 440 cycles per second. Like when you have to tune the strings on a guitar or something like that. Yeah, that guitar that's supposed to be vibrating at 440 cycles per second, it's not vibrating that fast, or it might be vibrating faster. Changing the tension in that string will cause it to vibrate either more or less, and that's where you tune a guitar or something like that. I do. Well, my kid owns my son owns a guitar, but it's a real guitar. Like, I mean, like other than just strumming the strings. So,
You should make a band.
Lauren, go ahead.
The pitch doesn't die out, is it singing is the pendulum?
Yes, it's exactly the same thing. The frequency of that pendulum will not actually change. Just how far it swings changes, which we'll talk about tomorrow. We're not going to get there today. Here's good.
So when you're like tightening the strings on a guitar, when you like tighten it more to just like make the string higher or whatever, it like vibrates back and forth like in a shorter distance.
Not a distance, it actually vibrates more times every second. It's not how far it goes, it's how much it's vibrating.
Well, wouldn't it, if it's like tighter, like let's say like a string's tighter than like another string, wouldn't like the looser string like go back and forth like I guess maybe farther back than like the shorter string?
No. It actually changes how often it vibrates, or how many times it vibrates back and forth. Okay? That's how it works, based on standing waves, which we'll talk about a little bit later. So, the one point I wanted to finish this off with, okay? If we're talking about something that's going at 440 cycles per second, recording the time it takes for one cycle is pretty hard. But if you know that it's vibrating 440 times in 1 second, can you figure out how long it takes for one vibration? That's pretty easy. You just take 1 second divided by 440. Okay? This is the frequency. But the time for one vibration, we said, was the period, right? period and frequency have an inverse relationship. If I know the frequency of something, right, I can figure out the period by dividing 1 over the frequency. Or vice versa. If I know the period of something and take 1 over the period, I can get the frequency. Those two things are inversely related to one another.
And it's also 1 second, like that.
That's what we do. That hertz, when you measure frequency in hertz, that's 1 second.